Consider a function of two variables. Let this be the graph of the function. This is z equals f of x, y. Now think of a point on the function. Say this is the point, and this point is a, b, f of a, b. So I have the point. The point is a, b, f of a, b. So it has three coordinates. Consider a tangent plane that touches the graph of this function at just this one point. What do I mean? Think of a plane that is sitting on the graph of the function, and it's tangent to the graph of the function at this particular point, AB, f of AB. Tangent means that it touches the graph of the function at just this one point, AB, f of AB. Now, there is a fact in mathematics that I could discuss with you, but for now I'm just going to state it, and we're going to maybe talk about it later. We're going to talk more about it later on, and we won't prove it now. So the fact is that the gradient of f at ABC is orthogonal to the tangent plane. At ABC. So in this case, we can regard f of AB as our C. So this point is AB, called as C. All right, now, so this means that the gradient, if you draw the gradient at this point, it's going to be orthogonal to this tangent plane. This is our tangent plane. All right. So the gradient would be, let's say gradient f of a, B, C. All right. Now think of any arbitrary point, any random point, x, y, z on the plane. That means that if you take the vector that goes from ABC to x, y, z, that vector is going to be orthogonal to the gradient at ABC. So what does this mean? All right. So this means that if we find a dot product of the gradient at ABC and the vector that I just talked about, that vector is going to be x minus a, y minus b, z minus c. We're going to get 0. The dot product of gradient of f at ABC and the vector x minus a, y minus b, z minus c is equal to 0. So that vector, if you call it p, right? P is just going to be x minus a, y minus b, and z minus c. This is equal to 0. But what does this mean? This means that the gradient at f of ABC is the partial respect to x of the function describing the equation of the plane, or sorry, of the function describing the 3D function describing the surface, if you take the partial derivative and evaluate it at a, b, c, and multiply it by x minus a, right? Or you know what? Let's do this. Let's look at the gradient first. This is fx, let's call it capital F, x at a, b, c, right? And then fy at a, b, c, and then fz at a, b, c. So this is a three-component gradient. And think about it. We can think of f. What is f now? Capital F. We can think of f as, we can let f be the function. So we can rewrite this as z. We have z equals to f of x, y. Or we can just say that, or z minus f of x, y is equal to 0, right? We can do that. Just bring it to the other side. So what I'm calling capital F is this function z minus f of x, y. Okay. All right. Because the function of 3 variables, since we're dealing with a gradient of 3 variables. All right. So if that's the case, then we're going to have that fx at a, b, c times x minus a plus fy at a, b, c times y minus b plus fz at a, b, c times z minus c is equal to 0. So this is the equation of the tangent plane that touches the curve at A, B, C. All right. And this is, we're assuming that the gradient is not equal to 0, but that's understandable. The gradient, if it's equal to 0, then nothing makes sense anymore. All right, so let's do an example to throw more light on this. Examples. Number 1, let's find the equation of the tangent plane at the point -2, 1, -3 to the ellipsoid x squared over 4 plus y squared plus z squared over 9 is equal to 3. Interesting. So this is our ellipsoid. And when I was discussing this, when I started talking about this concept, I started with discussing the graph of a function of 2 variables. The graph doesn't have to be the graph of a function. It could just be a quadric surface, for instance, like an ellipsoid is not a function, right? So in this example, we're not dealing with a function, even though we can always create a function out of an ellipsoid. So in this case, let's all start by describing what our capital F is. Capital F is x squared over 4 plus y squared plus z squared over 9 minus 3. Okay? All right, so if that's the case, maybe make it equal to 0. Just you're bringing the 3 from the other side. Let's look at our fx. Fx. Find the partial respect to x. This is just x over 2. Yes, x over 2. And fy. So I'm going to look for all the partial derivatives, and then I'm going to evaluate them at the point we're given. So fy is just 2y. Fz is 2z over 9. So if we evaluate each of this at the point -2, 1, 3, we're going to get -1 for that. Evaluate fx, fy at -2, 1, 3. We're going to get 2, and then fz, -2, 1, 3. We're going to get -2 over 3, I think. So that the equation of our tangent plane that we're dealing with, so if we now use this, formula, all right, so we'll be dealing with f at -2, 1, 3, and each of this -2, 1, 3, and that at -2, 1, 3, and this is going to be minus -2, so it's going to be +2, -1, and then -3. Okay, so fx at -2, 1, 3 is just -1. So we have -1, and it's x plus 2, and then fy at -2, 1, 3 is 2, it's y minus 1, and then f z at -2, 1, 3 is -2 over 3, z plus 3, z plus 3. What am I doing? I'm doing I wanted -3. All right, so let's put -3 here. Oh, sorry, I initially said -3, and then I'm doing 3. So I'm going to fix my problem, or maybe I should fix what I was doing, what I was solving. So -3 here, and this is -3. Yes, -3, -2 over 3. So this should give us +3. That should be +3. All right, thank you. And that is equal to 0. So you can do more. You can expand this a little further to get the equation of your plane. Essentially, you might want to put it in the form ax plus b y plus c z is equal to d, and then you find d, but I'm not going to do that. All right, I want you to try one. Try this yourself. So you have the equation. I want you to find the equation of the plane. Tangent to the paraboloid z equals f of xy equals 32 minus 3x squared minus 4 y squared at the point 2, 1, 16. All right. So I'm going to start it off for you by describing what your f, x, y, z is. So if you look at it, you can write your, if you take z to the other side, it just becomes negative z. So you can write it as 32 minus 3x squared minus 4y squared minus z. And this is equal to 0, something like that. Okay. So this is the function you're dealing with. And then you do what we essentially did in the first problem. All right, I would like to see what you got for that. Okay, let's discuss linear approximation. What is linear approximation? So again, if you remember in Calc 1, we did this a little bit. So in R2, if you have a function of one variable, say you have this function, this is a curve, all right? And you have a point, say A, and this is your x-axis and your y-axis is there, y-axis. Or maybe I should, let me make a curve that is, let me make something like this, okay? So this is not a linear function, but assuming you're looking for the value of this function, or you want to work with this function at a point A around this point, and you know that for everything you're doing, you're only going to be dealing with a very small interval around A. You can actually linearize this function around A. So what does that mean? You can find a straight line, the equation of a straight line that is tangent to this curve y equals f of x. This is y equals f of x at just this point, A. All right? So this is A and this is f of A. Okay. And we know how to do that. We know that the derivative f prime at A is the slope of the function. Is the slope of this line. So this is, its slope is f prime at A. So for that reason, we can just say that y minus f of A, so y minus y1, right? Because this point now is A, f of A. So y minus y1 is equal to f prime of A times x minus A. So this will give us essentially the equation of the tangent line. And this equation is usually easier to work with because it is a linear function. So this will give us, you can expand it a little bit further, you get y is equal to f prime at A times x minus f prime at A times A minus or plus f of A, right? Okay. Or you can, or maybe we don't even need to expand all this. Yeah. Or you can just go from this point. And just go from here. You could have just gone, this is just y is equal to f of A plus f prime at A times x minus A. All right, so this is better. This is cleaner to use. Now, in Calc 3, there's an extension for this in R2, in R3. So in R3, the linear approximation to the surface z equals f of xy at the point AB, f of AB is the tangent plane given by the equation z equals L of xy fx AB times x minus a plus fy AB times y minus b plus FAB. All right, we can actually derive this from the equation of a plane, but let's look at it as an extension of the linear approximation for 2D or for equation of a line in R2. Okay, so how can we see that? Look at this now. So look at this. This is for R2. Now, assuming I'm going to expand, I'm going to break this up. Assuming we rewrite this as, instead of just y, we'll write it as a function L of x, right? And I bring this, I rearrange this, take this here, bring this, no, this is plus, this was plus, it's not minus. Hold on, let me put it the way it was before I confuse you guys. So I'm gonna bring this to the front and take this to the back and put the plus where it is, okay? So okay, so this is R2, this is in R2, but I'm just gonna I'm trying to compare it to what we have in R3, what we're gonna be dealing with. You guys already probably see the comparison, so I'm gonna connect this to that, right? So that, all right, so this is that, and this is that, and this is that, right? Okay, so if you remember in Calc 1, you're always being told, hey, find the equation of the tangent line, right, at a point, equation of a tangent line. So you use that equation to find the linearization of that function. And that linearization is this. So we're saying now that in 3D, we can find the equation of the tangent plane and use it as the linearization of a function at a point A, B, C, or A, B, f of AB, right? And it's just an extension. And the extension, what makes it an extension, we're just adding an extra component because we're in 3D, right? Okay, so I'm going to keep this clean by erasing this. All right, so now let's look for a nice example to to wrap it up with. So call this example 3. Let f of xy be equal to 5 over x squared plus y squared. All right. We want to find the linear approximation. Linear approximation at the point -1, 2, 1. Okay. All right. So this is like our z. So think of this as your z is equal to f of xy, right? Is equal to, yeah, this is z equals to f of x squared plus y squared. All right, we're going to be using this particular equation. So for that reason, we need fx. Fx is just the derivative with partial derivative with respect to x. I'm going to do the derivative, and I want you to check that this is the correct answer. X squared plus y squared squared. That's what I got. And fy, -10y. So I'm doing it really quickly because I don't want this video to be too long. You can always check. So if we plug these things, if we plug in -1 and 2 into these functions, what do we get? So fx at -1, 2 is going to be 2 over 5. You can check it, 0.4. And fy at -1, 2 is going to be, I think, -0.8. That's what I got. You can check any of this. Pause the video, check it. If it's wrong, tell me that it's wrong. Send me an email or let me know about it in class. So again, we're using this formulation. We're looking for the equation of a plane. This is the equation we're looking at. We're going to use. So we need Lxy is going to be fx, let's do this, fx at -1, 2 of x minus a. Our a is -1, so it's just going to be -1 plus fy at -1, 2 times y minus 2 plus f at -1, 2. Okay, so we have 0.4 times x plus 1 minus 0.8 times y minus 2 plus 1. So that's what we have, Lxy. Okay, so you will see here that I use the squiggly sign. I could actually use that here. So let's put that squiggly sign here, and then I'm going to explain what it means. Right? It's squiggly because we're assuming that we're using this function L of xy to approximate the value of z, which is the value of the original function. That's why it's squiggly. This is the sign for approximately equal to. All right. So the next problem, or the next part of the problem, is we want to use linear approximation to estimate the value of f of -1.05 to 0.1. Now, before we solve this problem, I want you to notice this. Notice the point here. This is the point at which we found the tangent plane. That is the point. Now, with this tangent plane, we can find the values of this function for points that are very, very close to the point -1, 2 on the xy plane. All right? And why can we do that? Or why do we even bother about doing that? Because this function is actually easier than the original function. It might not look easier to you, but for the calculator, this function is way easier than the original function, which is 5 over x squared plus y squared. Here, for the calculator or for the computer, you are doing it, you're performing division, you're performing exponent, you're performing 2 exponents, you're adding them together and you're dividing. All you're doing here is you're multiplying and you're adding. Multiplication and addition are very easy, very computationally efficient. So that's why linear approximation is good. We're going to talk more about that in class. So in that case, we're going to say, oh, okay, this is, we're going to plug in, if we plug in -1.05 and plug in 2.1, so -1.05 and 2.1, and then 0.4, -1.05 plus 1 minus 0.8, 2.1 minus 2, and then plus 1. This is going to give you 0.9. Now, so this is the first answer you're asked to find. The next thing you're asked to compute is f of -1.05 and then 2.1. If you do that, I did it and I got, that's 5 over -1.05 squared, right? Plus 2.1 squared. I did this and I got 0.907. So they're close. So this is telling us that this function, 5 over x squared plus y squared, can be approximated using the tangent plane at that given point, right? -1 to 1. Okay. All right. We're gonna stop here, and I will see you in class.